Very well. So here we are. This is a continuation of the previous talks. So I will go rather quickly about the first little part. That is what we saw last time. And I'll start with the new part that is about loop orbifolds or loop groupoids. Just as one can define the free loop space of a topological space really, but maybe a manifold, as the space of mappings from the circle S1 to your manifolds. And this has proved to be a very useful concept in both topology and mathematical physics. Perhaps the unifying theme in what I'm going to say today is this loop orbifold of an orbifold. There is a slightly more subtle concept. Is no longer just, well, it wants to be just this mapping space, and in a way it is. But because an orbifold in many ways is already a category, a groupoid, its loop groupoid is as well, the loop space of an orbifold is an orbifold itself. So it's some sort of category as well. And it gets a little bit more interesting. So again, a groupoid, traditionally for a group, X1 would be just a point, would be a set with one element. And X0 would be the group. X0 would be the X0 would be the set with one element. And X1 would be the group itself. And here where the source and the target maps, every arrow of a group goes from that one element to that one element. And then you would have the group structure, the multiplication of arrows, the inverse of an arrow. You mean every element of the group as a little arrow going from one point to itself, actually. And the identity is this mark point. You can think, actually, that this point is the identity of the group. This one element set is the contains just the identity of the group. That would be for a classical group. For a groupoid, though, now we could have many identities, so to speak, well, and then you would have to make sure that the tip of one arrow is at the tail of the other to be able to compose them. And that's a groupoid. And we're modeling orbifolds by Lie groupoids with additional characteristics. We're asking that all these maps are local diffeomorphisms, that all these sets are actually C-infinity manifolds, and more or less that that they are also proper maps to avoid infinite stabilizers. So we already saw that orbifold K-theory was formed with equivariant vector bundles or orbivector bundles. Last time this was a vector bundle, and it was over the set of objects of the groupoid. And this isomorphism was equivalent to having an action of the local groups. And then you form the orbivector bundles and the K-theory. And this was the same if you had just one group acting on a manifold as equivariant K-theory. This is just a review of what we had last time. Well, now let's move on to the content of this new talk. And the way to go about it is to consider the Laplacian. This is kind of, the Laplacian is a toy model, a toy version of a quantum field theory. So I'm going to consider the Laplacian as the simplest version of a quantum field theory. For this, we have to introduce a metric. And as always, first we recall the situation on a manifold. And then we see what happens on an orbifold. So you have the Laplacian, but traditionally in basic classes, the Laplacian will act only on functions, but it's very natural to extend the Laplacian to forms. So it acts on K forms. And this Laplacian contains the information of a quantum field theory. So a quantum field theory has to have a fields that are being quantized. The space of fields, which is a topological space or an infinite dimensional manifold, well, this space of fields is quantized so that functions on this space of fields become operators on Hilbert space. This is the basic desideratum. This is what we would like to have, some sort of operators on Hilbert space that mimic in a non-commutative fashion functions on the space of fields of the quantum field theory. Now, space of fields are typically these infinite dimensional spaces. And for the Laplacian, the space of fields is just the space of maps from the interval or the circle. Here is a typo. From one-dimensional manifolds, you have the space of maps from the interval to the manifold, and that's an infinite dimensional space. And that's sort of the space of fields in this theory. You are to think, maybe fancifully, that these maps from intervals to the manifold are paths in this Feynman path integral approach to quantum field theory. So our histories, these are the space of histories of a system. So you have the space of histories, and this topological space you want to, and the functions on this topological space are things that you want. Functions on these are values to every history of the system. And then you have all these histories, and you have all these values to every history of the system. You have this space. You want now to quantize this world of histories into a quantum system that includes the H bar, the quantum world. So operators on a Hilbert space that correspond to the space of histories. Let me stop here. Is this more or less clear?
Yes.
Very well. So we have the histories. Given a history, one of these paths on one of these manifolds. Maybe I fix the manifold, fix the manifold. We have to have a Lagrangian for the so-called Lagrangian for the theory. And a Lagrangian for the theory is something to every history it assigns some sort of thing that we want to sort of optimize, So there is this Lagrangian, and then in the classical world, I would get the Euler-Lagrange equation for a history, and solving this partial differential equation, I could get a deterministic history, the history that optimizes this. But in the quantum world, I have to sum over all these histories to obtain something that resembles evolution. And it turns out that this Laplacian becomes important for this one Lagrangian, because I said I wanted operators, and these operators are going to be the analogous to the observations in all the possible histories. And this Laplacian is going to give you the evolution of every operator in time given this Lagrangian. So And because the exponential of e to the I, this operator, gives you the evolution of observables that are now operators on Hilbert space associated to this Lagrangian, it is really the entire evolution is given by this operator. It gives you the time evolution. This operator gives you the time evolution of the quantum system. But really, it's only the spectrum that gives you the time evolution of the quantum system. And so the information of such a quantum theory is contained in the spectrum of the Laplacian. Is that okay?
Yes.
And recovering the classical theory, and of course, it is a theorem that it is precisely this operator that gives you precisely the evolution to precisely this Lagrangian. I'm not going to prove this, but this is not hard. Formally, at least, the analysis can get a little bit elaborate, if not hard, elaborate. You know, you have to get the right spaces in the adequate table of space and all the correct thing for the thing to be rigorous. And in one dimension, in this one-dimensional kind of theory, it almost is rigorous. You know, it's kind of Brownian motion, but recovering the classical theory from the quantum one is here in the shape of a drum. You see, there was something happening what I just said verbally, and I perhaps should have elaborated this a little bit more. But now I want to have these operators, and this operator, and the operators evolving according to the exponential of this operator in time, e to the I, t, these, some pi somewhere here. So you take the exponential of I, this operator, h bar, this operator, h bar I, this operator, and this gives you a time evolution of any other operator. Something was lost, actually. Different quantum classical systems, this is the Lagrangian of a classical system, could conceivably give you the same set of operators and evolution and numbers, observables that are given by eigenvalues of these operators and so on. The whole quantum system, the whole gadget of the quantum system could conceivably be obtained by a different manifold. The input was a manifold. That was a Riemannian manifold. That was the input of this story. So the question, well, really, are you going to recover different manifolds? And because all the information of the quantum system, I said, is in the Laplacian of the operator, recovering the manifold just from that set of numbers seems like a too lofty of a desire. You know, it sounds like an impossible task, you know, but surprisingly, very often it can be done, and it's actually hard to find a counterexample where it cannot be done. This is surprising at first. And this is the task of recovering the classical theory from the quantum theory. Yeah?
Yes.
And this is called by more classical mathematicians that are skewed in the mention of quantum things as here in the shape of the drum. Because it could also be interpreted, this task, as well, this famous problem here in the shape of the drum. But I prefer to think of it today as recovering the quantum theory from the classical one. So the Feynman integral path integral formulation approach to the theory it tells us that computing integrals over the free loop space of the manifolds and using a stationary phase approximation, one can find a path from this input, the manifold with a remaining metric, to the spectrum of this operator. And this is by performing this kind of fanciful Feynman integration. That again, if the manifold is one-dimensional, this can be made rigorous. Of course, one-dimensional manifolds are unusually simple. But if the manifold is one-dimensional, this is the Feynman cats approach, and this can be done rigorously. As soon as the manifold O is 2-dimensional or higher, and let's not talk about 3 or 4 dimensions or 5 dimensions, the task gets more and more formal and less analytical in nature. You can do for mathematics, but they will be of a formal nature, and less analysis will be missing from the picture because it's too hard, and we don't even know if it's really there. So the partial differential equation is related to the, well, I mentioned this is the time evolution. Almost, it's missing an I. But there is this trick of the weak rotation that, well, you just put the I and then you say, okay, well, it's missing an I, but I'm going to think of these because of the analysis. It gets easier. It's much harder, the analysis, if you have the I here. So I'm going to think of this and then hope for the best, about this missing I. And then what you get is this partial differential equation that is that gives you the solution for this evolution, and this is a form, of course, a K form. And now the fundamental solution for the trace of the heat kernel. So you want to understand this evolution, so you take the trace, and then it turns out that it's what I promised, that the Feynman integral of this e to the Lagrangian, and this is kind of an h bar, this t, is actually related. This is the relation that I promised to the spectrum of the operator. This is the relation between the Feynman integral and the spectrum of the operator. And this is, again, if M is 1-dimensional, you can do it with the Wiener measure and so on. If M is higher dimensional, it's much harder. Any questions up to now?
No, it's more or less clear. So.
And so it turns out that the sum of the traces is independent of T. And the long time limit of this sum equals the Euler characteristic of the manifolds. By recalling the theorem of Hodge, which identifies the k-Betty number of M as the dimension of the kernel of the operator. And the short time behavior is given by an integral on a. So you localize this integral. You say, well, this integral, where does it take the most relevant values, And in the limit, what you get is this. If you elaborate the previous discussion, for example, for the 2-dimensional manifolds, it still can be done. This equality of long and short time behavior, T, of the heat flow, gives you on the one side the integral of the curvature, and on the other side the Euler characteristic. And so you recover this profound theorem of Gauss, telling you that the Euler characteristic of a manifold is the integral of the curvature. It's a very beautiful story. And we want to build on this story by taking more elaborate Lagrangians, not such a simple Lagrangian as this one, but a more elaborate Lagrangians on the one hand, and on the other hand, by changing manifolds for stacks, so-called stacks, or say today orbifolds, or by putting a group action on M, whichever way you want to think of it. So that's what we want to do. We can do much better than simply recover the Euler characteristic. That's what I want to say. Suppose that M is spin manifolds. Then we can recover by this same procedure the index of the Dirac operator. And again, The Laplacian is an operator. The square root of the Laplacian is the Dirac operator. It was an enormous discovery of Paul Dirac, the existence of this square root of the Laplacian, and it produced one of the most fundamental mathematical discoveries of the 20th century. That's the Dirac equation for the really the advent of quantum field theory rather than quantum mechanics. But from our geometric point of view, we want to be geometers, and we will need loop spaces. So let's see what happens with orbifolds. We want to generalize all these to not the Laplacian, but the square root of the Laplacian. And the generalization from the Laplacian to the square root of the Laplacian, while sounds rather innocent at first, is a deep one, because it will give you the so-called Atiyah-Singer index theorem, one of the top achievements in mathematics in the 20th century. And it's just generalizing from the Laplacian to the square root of the Laplacian. This square root can only be taken in a well-defined fashion if the manifold is just as the Laplacian was nice if the manifold was orientable, really, namely the first Stiefel-Whitney class vanished. This square root of the Laplacian can only be really made sense of nicely, and there are things you can do, of course, but if the square root of if the manifold is spin, namely the first and the second Stiefel-Whitney class of the manifold vanish. And now Bernardo Uribe and myself introduced the analog to the loop space of a manifold for orbifolds. The idea is that to a groupoid, a Lie groupoid, an étale proper Lie groupoid, we must assign a new groupoid or new infinite-dimensional groupoid that takes place of the free loop space of M. So we have a category, we have to define the loop space of this category of a geometric type. And our construction furthermore commutes with the functor of classification that I explained a couple of times ago, from groupoids to spaces. And Uribe, Jicotenca, and myself proved a beautiful statement, that is that classifying the loop orbifold is the free loop space of the classifying space of the orbifold.
And when you write equivalent or isomorphic, what does it mean exactly?
Well, they are topological spaces. They're actually only homotopy types, and what I mean is homotopy equivalent.
Okay.
You see, the classifying space of a groupoid is already just a topological space, actually a homotopy type of a topological space. And the free loop space of a homotopy type is a homotopy type. The free loop space of a topological space is a topological space. So I claim that these two topological spaces that are very different in apparent form are actually homotopy equivalent.
Yeah, beautiful.
So this is very nice and very useful. But let's make this a little bit complicated, because of course for stacks this gets it's in one of our papers that it's called groupoids. But in the case of a global quotient, it's simple, so I can explain it. So say that the orbifold is just one manifold divided by just one finite group. Literally, it has only one chart. Of course, this manifold could be compact. This group quotient could be compact, or non-compact or anything. So I have to define a category that is geometric, so that the objects are a topological space, actually an infinite dimensional manifold. So Lx, the objects of Lx, is going to be the union, the joint union of paths that satisfy this condition, that have G periodicity, G holonomy, with respect to this G action on M. So in the past, the loop were closed paths, but now they are going to be closed up to the action of a G for every possible G. You see what I mean?
Yes. Yes.
And the arrows are going to be these pairs. This I'm going to denote by gamma comma G, an object. An arrow, well, is G gamma comma G comma H. And gamma comma G, this arrow sends gamma comma G to gamma to the whole path translated by H, and then G conjugated by H. And this is a very important point of this talk, this conjugation. Because this is what it looks like. This is what a loop looks like. It's a reasonable thing.
Mm-hmm.
So this object is related to this object of this category via this arrow. So the loop groupoid is a category of this a loop. It's a loop, category of loops. And this is the Orbifold localization. With this definition, it's very clear. This simple, but it has a lot of implications. The Orbifold localization principle theorem. A very important fact to localize the integrals in the Feynman-Katz case or in all these things that I told you about before was that if this was a manifold Lm is 1, the fixed points, the fixed loops on the rotation of the loop space was M, just the manifold. What is the big surprise here, or the surprising thing here, is that Lx is 1 is the inertia by definition. It's no longer, but the whole point is that it's no longer X, is that something else. And the definition of that something else is this. And these, its objects are automorphisms. So is the category of automorphisms of the original orbifold.
Okay.
And the arrows is kind of the center, you know. This is what an arrow looks like in this orbifold. Now the objects of the orbifold are these arrows, and the arrows of the orbifold are these conjugations. And this is the fix on the action of S1, the fix orbifold of the free loop orbifold of the orbifold. Is this more or less clear?
Yes. Yes.
Very well. So, well, for a smooth manifold, we have this, and this is very used in all this theory because you localize integrals from here to here. You typically localize integrals from here to here in quantum field theory. In orbifold quantum field theory, you localize integrals from here to here, not to here, and that changes the whole structure of the theory. So, for example, remember the Gauss-Bonnet theorem that I was talking about? It was giving you the Euler characteristic of the manifold, remember?
Yes.
Well, now I will give you the Euler characteristic of this object, and this is called the orbifold Euler characteristic of Conway and Thurston. So you recover in this way the orbifold Euler characteristic that Conway and Thurston obtained thinking like on games and things like that, you know, with fancy notation and cleverness. Now you need not to be clever. You just do the Gauss-Bonnet theorem under this localization for the Laplacian, and you get the orbifold Euler characteristic. Very nice. In the mathematical literature, I of x is called the inertia orbifold. In the physics literature, it is called the twisted sectors. The classical geometric mathematics. Well, I'm being unfair. The twisted sectors are the quantization. Remember, we wanted to quantize the loop space, to have a Hilbert space and operators that corresponded to functions on the loop space. Now, there's a bit of a surprise, though. This is a loop space. It's a small loop space, but no, it's finite dimensional, and it can be quantized. And this quantization is what physicists call the twisted sectors. But because this is finite dimensional, even the cohomology of this space is a reasonable quantization, and then it has all this twisted sector structure. And the localization, and of course, these I of x, mathematicians define like this, by fiber products and whatnot, and traditionally they do not use the loop space. My definition has the advantage that justifies this feeling that this is stringy, because, well, it's part of the loop space. And the ordinary Euler characteristic of this is the orbifold Euler characteristic of Conway and Thirst. So we have found something nice. Also, the orbifold K-theory of equivariant Siegel's K-theory localization with characters, thinking of this as representation theory of the groupoid. Well, this is like the class functions. The ordinary K-theory of the inertia is like the class functions. So this is an isomorphism. You see what I mean?
Yes.
So this is another of our observations. For global quotients, there is many ways to represent this, and this is one way. This is one possible way. And this recovers Siegel's localization formula and the Euler characteristic from the previous talk. Let me just say that this inertia has a classified space as well, BIX. So one would like to know what is BIX. That is the joint union of the Borel constructions of all these group actions. This is the centralizer of G. Sorry if I didn't say it. Centralizer is the ones that commute with G. So, well, you can define the Gauss loop space, we did in a paper called Gauss loop space, of Bx, of the classified space of the original category X, as those loops that project to a point in the quotient space of X. That project to a point. And I call it the Gauss loop space. You know, there is this X, on top of it there is this Bx that is enormous. On top of every point X in X here, there is the classifying space of the stabilizer of X. So it's BGX for a little BGP. A little point here. The fiber of this map is typically an infinite dimensional space. But if the whole loop lies in BGP and doesn't move from BGP to BGP prime, if it loads entirely in a BGP and projects to a point, I call it a ghost loop. Because I don't see it here. I don't see it in X. It lives here, in this ghostly realization of X. And then this is the ghost loop space. And this theorem that we prove is that the classifying space of the inertia is the Gauss loop space. You see what I mean?
Yes, beautiful.
And so the Euler, by the way, the Euler characteristic of this thing is the Orbifold Euler characteristic because everything else is torsional. So this is stringy. So the correct Euler characteristic is stringy. The Orbifold Euler characteristic of Thurston. Come on, Thurston, they didn't know it, but it's stringy. Is the outcome of this stringification of even the Laplacian. The Gauss stringification of the Laplacian. And I will stop here because now I will move into algebraic geometry. I will leave the realm of quantum field theory, operators, and topology, and I move into the realm of algebraic geometry. So I will continue next time with the algebraic geometry. That's all for
Yeah,
today.
amazing story. Thank you.
It's a nice story. It's a nice from that we were doing in the 2000s, early 2000s. But now this has a revival for several reasons. And I'm talking a lot to Anatoly Leibgover and so on. I'll tell you about that. So that's all for today. It's so good luck with your crabs, Nikita.
Yeah, by the way, maybe you can stop recording.
Ah, sorry about that.